So we won't do any eye candy today. Hopefully you had a nice break. What I did plan to do is run at 30 speed through what you might have already looked at on Monday. Obviously we had a holiday on Monday, but there was a class, and so usually there's 2 straight weeks at the beginning of semester before Labor Day. Sometimes it's 1 week if we start late for some reason. And so in 2019, apparently, we were here on the third Monday of the term, just because of the way the Labor Day must have been the week before, I'd imagine, in that particular case. And so we had a class, and so this is the recording from then. And so if you looked at this, we've moved from looking at pressures at a point where we know that dP dz is equal to minus the unit weight of the fluid everywhere. And we can use that to be able to integrate it vertically, either in an incompressible fluid, in which case we have one relationship for the pressure changing linearly with depth, and for compressible fluid, where we have it as a fluid that the pressure changes non-linearly with depth to an asymptote as we go up in the atmosphere, for instance. And so this is some exposition of this as we start looking at pressures on structures. So last time, one of the videos we looked at was the Malpasset Dam. Filled up the dam. Pressures acting on the back of this thin arch dam were big enough to rupture the abutments, and everything flowed downstream and killed a lot of people. Another exposition of this would be, for instance, air traffic or air travel. And so this is one of the first commercial jetliners, the Comet, de Havilland Comet in Britain. Quite an elegant plane. You see that the engines, not very practically, are embedded within the wings. And its problem was that lots of the flights actually didn't reach their destination. They just disappeared in the days when radar wasn't so well developed. And it turns out that the problem was that the plane had rectangular square windows in it, and square windows act as stress concentrations. And when you go up and down in the plane, these pressurized cabins, I said the other day, I think they're pressurized to 6,000 feet equivalent. And so if you go up to 35,000 feet, there's a big difference between the air pressure inside, which is higher than that outside. And so that fatigue loading in landing and taking off was something that was slowly making cracks grow from the corners of these windows, and the planes would just break up in flight. Not the kinds of flight you want to be on, of course. And so it was a big mystery until they finally figured out what was going on and redesigned the windows. And of course, if you fly in a jet these days, all windows are nice and oval and round. This is much more recent. That's the 1950s. This is one of Aloha Airlines, and you kind of see what's going on. Not the flight you wanted to be on, an inter-island flight in the Hawaiian Islands, Aloha, you'd guess. And again, the same thing, salt air maybe. I'm not sure that aluminum, which skins of these planes are made of, corrode very much, but certainly pressurization, depressurization multiple times a day, and fatigue cracking. And so not really, you want to be flying along and have the fuselage above you just disappear. So I know, one or two people died, the flight, the cabin crew. I remember one cabin crew being held onto by a passenger so that they didn't fly out and landed safely. Not the thing you want to do, to be able to look below your feet and be able to see the runway come up, I think, as you land. So this is probably 90s, I'm guessing. And so what else? Malpasset Dam we talked about. Vaillant Dam is another dam in the Italian Alps, where rather than the disaster resulting from a landslide falling into the dam, displacing all the water that was impounded behind the dam over the top of the dam, but the thin arch dam was so strong that it resisted the impulse from the water hitting the back, but still overtopped and killed 15,000 people or something downstream. So that's kind of the motivation for this. We'd like to understand what pressures on structures are. So the Malpasset Dam moved, ruptured, and then went downstream. The Vaillant Dam survived that impulse on the back. How do we solve problems where we look at pressures on structures? And so I'll go through this. You can't do this on YouTube. You can only go through double speed. But so continuing from last time, we talked about the rules that we have, that the blue curve is for incompressible fluid, the green curve is for a compressible fluid. dP dz is equal to minus unit weight is always true, but when you integrate it, the way you integrate it changes. And so what we'd like to know is, one, if we're resolving the forces on bodies, what are the forces that are applied? In other words, number one up here, and we can get that, as we'll see, from a relatively simple expression. Where do they act? Because in some cases, we'd like to be able to say what the free body diagram of the structure they act on is, and what failure mode do we expect to occur is kind of the third one. So we'll talk about those today. So this is just a little example. If you've looked at this already, great. If not, you could take the fuselage as being a circle. You could make it into a free body with some kind of cabin pressure inside it, some kind of atmospheric pressure outside it, and you could isolate it as a free body. Again, I'll repeat for this class, when you can think in terms of those, that's the key to this class, is being able to imagine exactly what these structures look like. A free body just has the cabin pressure acting upwards on the structure. It has the air pressure outside acting downwards on the structure if you just draw a line straight through it. And so you can just reconcile those two forces acting against each other. So there's a net upwards force because the blue area under the curve is bigger than the red area under the curve. And that has to be held down by the tension of the metal on the skin of the fuselage. So the tension of the metal on the skin is these two forces here. It's equal to the stress times the thickness of the skin times the length of the fuselage into the page, divided by the area of the segment. And if you go through that calculation, you can solve for the thickness, and it comes out, if you do that, to be something like 2 millimeters. Not an unreasonable magnitude for the tensile strength of aluminum. I could imagine that would be roughly the thickness of a plain skin. Certainly, it's not 5 millimeters, I wouldn't think, or 10 millimeters, and not 1. 1 sounds kind of too thin. So a reasonable number that you can get out of it. So that's what we're interested in doing. So the rest of it is talking about pressures on structures. I'll probably go through this again today. But again, if we can look at the distribution of pressures with depth, we can merely integrate that. And we spent some time talking about how you take a little slither, dz, that has a pressure acting on it, and you integrate that slither vertically, so you can sum up all the individual slithers of pressure. That's really all we're doing. And if you do that, you end up with a resultant force, which is equal to that, which we can redefine uniquely as that expression that we'll use today. And so the force that's applied on any flat structure, independent of whether it's vertical or inclined, is equal to the unit weight of the fluid acting on it, an incompressible fluid, times the area of the plate multiplied by the depth of the centroid. And so the depth of the centroid for that plate would be, if this is the plate, if you draw a line from corner to corner, or the balance point, if you like, of this, would be the balance point of this particular sheet. And so the centroid of this, center of gravity, if you like, is the point where it would balance if it wasn't bending over. And that, whatever that depth is vertically above the surface, is going to be the height of the centroid below the surface. So that's one thing that we'll deal with. So if we have that, so that's always the case for an incompressible fluid. I said 30 speed, I'm only running 20 speed right now. And the reason for it is exactly that. If you think about an inclined plate, one part of the plate is less deep and has a lower pressure. One part of the plate is more deep and has a bigger pressure. If you draw the line between that, the average pressure is going to be at the center point. That's all. And so if you look back at this diagram here, if I go back, this diagram here, the real pressure distribution is given by this blue curve, blue line on this. If you take the average across the length of the plate, in other words, you take this triangle here and this triangle here and move one to the other, then you're just representing the average pressure here, which is HC gamma W. This is this, gamma HC is the average pressure, and you're multiplying it by the area, exactly this expression. So try and visualize, if you like, what these things are that are going on. Don't need that. What else? What else? So the other thing is we'd like to know where it acts. And again, this is a bit more arduous a derivation, but it ends up in a standard result. And maybe we spend some time talking about that, but we really just want to use the standard result. And so I will probably skip this, but the idea is we want to know, one, the magnitude of the force. The resultant force acts perpendicular to the plate. It's F sub r. The location where it acts is at some depth, y sub r. And we need some method of being able to determine exactly what that is. And so that's our job for today. So I don't know exactly why nothing worked, but that finally worked for us. So that's where we're going today. Right. So we're back on track. So, right. So what we'd like to be able to understand is, if we do, this is the force that's acting. It's always true for an incompressible fluid and a flat plate, and it comes from the fact that we could draw a system, and I'm going to draw this system. I'm just going to not worry so much about the derivation, but I'm going to draw what the system is that we're looking at. And so I'm interested in having a coordinate system where this curve sits on the top of the water that we have. And this curve will be, say, in the x direction. And this curve is inclined below the surface of the water in the y direction. And on that we have some kind of plate that exists that I'll draw like this. And I'm going to use my, is it this one? Is this the marker? Yes, this is it. So I'm going to use this to represent the plate. Oh, this is art. So the geometry we've looked at is a plate that's below the surface. And so we want to be able to define some characteristics of this plate. I said already that we're interested in the centroid of that plate. And so I'll put these on. The centroid of this plate is exactly at this location. So you can imagine balancing it on either of these knife edges, just the plate without the water on top of it, and it would exactly balance because there would be a lever arm of this amount of weight times this lever arm here, and it's exactly balanced by the same lever arm on the other side. And if you sum up all those lever arms, that's exactly what it means that it's balancing, right? You have a plate, the weight of this part of the plate here acting through the fulcrum is the moment. The weight of this part here acting through the same fulcrum exactly counters it. And so the weight of it is uniform, and therefore it's in the middle. So we can then, and I can't draw this very well, whoops, is that the depth of this centroid below the surface is what we've called h sub c. So if you imagine this surface being here, I can't really draw in 3D, we know that the force that's acting, the resultant force acting on that plate, is the unit weight of the fluid times h sub c multiplied by the area of the plate. So obviously, not obviously, but h sub c times the unit weight is the pressure. Those two terms, right? Unit weight times depth. It's the pressure at this point, and therefore, from what we said before about the distribution, that if you have a plate that has a distribution of pressures on it, which is shallow, small at the top part, bigger at the bottom part. These are the distributions of pressures. Then by definition, in the middle, this value here, P is equal to gamma HC. And so this would be, this is the water level. This is H sub C. That's all it is. Nothing more than that. So we know exactly what the magnitude of the force is, and I could draw that force on it, but it'd probably complicate it. It's a force that's acting across the plate like this. And I deliberately didn't draw it at the point of the centroid. It's somewhere offset from that. And so this magnitude of the force is offset from that. And the reason for that is that if you, I won't go through this derivation, it was in your stuff on Monday if you've looked at it. We can also take the magnitude of the force and we can derive it and we end up with this expression. What we can also do is we could take moments around any point. So for instance, we could take the moments around here. Red would be a better color. We could take a moment around here, which would be this. And so we'd take this differential distribution of pressure acting in this multiplied by this lever arm. We'd take this differential distribution of pressure here acting by this lever arm. And of course these lever arms are of length y, and these lengths are dy. Doesn't really matter. And so all that matters is that if we take the moments acting around here, we can also do it differentially by doing that, but we can also do it by looking at the magnitudes of the forces. So the moment around here has to be equal to the differential pressure multiplied by its lever arm multiplied by the area which it acts on. So this is the lever arm, this is the magnitude of the pressure here, and the area it acts on is this area here. Area is equal to x dy, I suppose. So that's what this is. No, not x dy, y dy. No, x times dy. And if we do that, we end up with a differential multiplied by this, which is also equal to this force multiplied by whatever that lever arm is. So we're going to call this y sub r times f sub r, right? So incrementally, or finitely, I guess, y sub r multiplied by f sub r has to equal the moment by definition. And so if we can calculate this as a differential, and if we know what this force is from F equals gamma HCA, so if we know that, then we can solve for this. That's all we're doing. And so if we do that, we can solve for this. It's a standard result, and the standard result is exactly this. And that's all you need to know. And it's given by, so the lever arm YR is equal to the second moment of area about the surface divided by the area times the slope distance of the centroid below the surface. So it's in this plane. So if we're drawing on this diagram, which I'm going back to, this length here would be y sub c, the slope distance. HC is vertical. And so if also I draw it out here, this would also be y sub c. But it's more convenient for us to not write it in terms of the second moment of area about the surface, but to write it as the second moment of area about the centroid and relative to this. And so the second moment of area relative to the centroid is not relative to this surface, but is relative to the location of the centroid. And so what we could write this equation as here, and I will write it, is y sub r is equal to I xc, which is just a result, divided by the area yc, plus a yc squared over a yc. And the reason for writing that is that we can get rid of this, and we can get rid of this, we can get rid of this, and we can get rid of this. And so it becomes this standard result times y sub c. And so we can think of this length where the force acts as being equal to the location of the centroid plus some small amount. And so it's easy to draw on this as this. And I'm going to call this small amount, actually I'll write it in line with this because I can. I'm going to call this delta yr. And so that together, these two things are equal to yr. And yr we just wrote as whatever it was up there. I'm going to write it exactly the same, ixc. Again, just a standard result plus yc. And so you see that this location where it acts, so this is the point where the force will act, and I probably will draw the force then acting up. So the force will act perpendicular to this plane. It will be of some magnitude f sub r, and it will act exactly at this point here. We've only said where it acts on this axis, but just from the symmetry, you know it has to act on this. And so the reasons for that, I guess the reason this is called the second moment of area about a centroid is if you look at a flat plate where, I guess this is the y direction, and if you look at summing up all the moments as you go along here about some magnitude, you get the first moment of area. If there's a distribution of the thickness of that plate, there's a density that changes linearly, so that weight is equal to a constant times y. That's what the equation of this is, right? This would give you the second moment. So this one would be the weight is equal to a constant. This would be linearly. And I guess the third moment, if you like, just as understanding this terminology, the third would be, I guess, w equals a times y squared, etc. All you're doing is you're taking the lever arm, and the fact that the pressure distribution changes as you go with depth, it increases, that you have an increasing pressure distribution, and that's the reason that if you think about it, it has to be below the centroid. The pressure here is small, the pressure here is larger, so if you're taking moments of a length times an increasing pressure, it's weighted towards the larger pressure at depth. That's all you're saying. If the plate was exactly flat, horizontal below the free surface, then the point of action would exactly be the centroid of the plate, because it would be a linear distribution of pressure just like this. So that's kind of rationalizing it. So as a standard result, it's probably good to understand where it comes from, but it's probably more useful to understand exactly what the expression is that you need to use. So the force is equal to this amount, and we'll do some examples to kind of cement it in your brains. So these are the two standard results that you'd want to be aware of. And the magnitudes of these terms, they come out to be terms like a proportional to y cubed in this particular case, etc. So these terms are given to you in your textbook, or they're given to you in these notes. These are just they. So these are standard shapes. The shape we've just looked at is a rectangle. The area is equal to b times a. The second moment of area about the centroid is 1/12 of the width times the depth along the slope. So A is the slope in our particular case. So if we drew that on our diagram here, this would be our A. And this would be our B. And it's divided into B over 2 because it's relative to this centroid. So these are standard results. And so all we need to know is what they are and how to be able to use them. So the one we're interested in is this one here. No, sorry, X. What was it? It's Y. Make sure I transcribed it properly. X, see, yeah. So we're interested in the X. It does matter which they are. So it's equal to this one here. And the first example we'll do, actually we'll do with a circular one just because it's different. So this one, the standard results, by definition, they have to be units of length to the power 4. You see that they're all units of length to the power 4, apples to apples, etc. And these are standard results for different things. This is the centroid of this shape. It's the balance point. This is the point that we'll calculate our point of action relative to. So let's do an example. Right? May look a bit complicated, but those are the two equations you need. All right? What else do I need to say? Nothing. I guess if you think about this, it has to be on this center line going down here, because as you go across here, the pressure doesn't change. It's different at the top than it is at the bottom. It's bigger at the bottom, but as you go from left to right in the x direction, it stays constant. And so the balance point will be symmetrically in the middle here. It has to be on this center line as you go down. So let's do an example. So the example is exactly this idea of having a gate here that's below the surface of the water. The gate is on a fulcrum, which is this point here. And I guess we could take forces around here. And one point I'll make is that this gives you the resultant force. This gives you a location of action. And I'd say the third thing that we want to be mindful of is what I call a failure mode. So for the plain skin thing, we decided on a failure mode, that it was going to rip the skin in tension apart so we could draw a free body diagram. So we also want to be able to define those for our systems we have, some mechanism by which it might deform. And so therein lies some art in what we might want to do. So here's an example. So we have a gate below the surface of the water. It's circular. There's a hinge that goes through this midpoint here that allows it to be able to rotate around this hinge. And we have a backstop here to stop it from rotating. So if we think about if it's got water on either side, we could imagine that it would have a distribution of pressures on it acting that would look like this. It's not a zero pressure here. This pressure acting up here would be what? This would be equal to P is equal to, I think it's what is it, a 5 meter radius gate. So this would be 5 meters times unit weight of water. Interestingly enough, it would have exactly the same, if it had water on the other side, it would have exactly the same force acting on it. And it would be in equilibrium because these forces would be the same. And so from what we know about this distribution, we could surmise, we know that we can calculate the pressure because if we wanted to, we could look at taking this area, we could take this area down here and we could remove it and it would exactly fit in this area here. Right? We know that. But we know from this distribution that the location of action of this is somewhere below the centroid, from what we just said. And so if the location of action from this is that the resultant is acting here, the net moment of this is going to be trying to turn the gate counterclockwise. So if we remove this water from here, so there is no force acting against it, because there's a net force acting here, the only thing that will keep it in place is if we can apply some force by this backstop here. And so the question is, what force do we have to apply here to stop it rotating? And we can rationalize that that is what it's going to do. And so what we'd like to do is calculate two things. We'd like to calculate what this force is, and we'd like to calculate what this lever arm is here, so that we can calculate exactly this force times this lever arm is equal to this force times this lever arm. So that's where we're going. So how do we do that? We know that the centroid of the plate is this standard result. I'm going to write down, and so it's going to be from this standard result that we looked at. Obviously, you have a saucer, a basketball, you can balance it on your finger. The point of balance is the centroid for all the reasons we've talked about, and that's going to be this location here. The area is just by pi r squared, and this second moment of area about the centroid is the radius to the power 4 pi r to the 4. So what we'd like to do is calculate exactly where that is. We know that the force, the easy one, is the resultant, which is going to be equal to the unit weight of water times the depth of the centroid multiplied by the area, pi r squared. What's h sub c? Depth of the centroid, it's 10 meters below the surface, and so this is 10 meters. And this is 9.81 times 10 to the 3 newtons per meter squared, cubed, sorry, right? So we know easily what that magnitude FR is, and it gets calculated down here. That's this. But we want to know where it acts. So we know it doesn't act at the centroid. It either acts at the centroid or below. If this was in contact with the surface, there's a good chance it might act at the centroid, but it doesn't. It would act slightly below. And so we want to calculate the center of pressure. Center of pressure is given by the second moment of area about the centroid, the slope distance of the centroid below the surface, and the area, and the slope distance. So if we go back to this figure, the slope distance is in the plane of this. If the plane was inclined, it would be an inclined y. If the plate is vertical, it's a vertical y. And therefore, it's actually, yc is going to be what? 10 meters, right? I guess. A is going to be pi r squared. YC is going to be 10 meters. In other words, it's just the balance point of this plate, which is actually a hinge. And it has to be in the center of the plate, just from symmetry reasons. And this standard result is that this is equal to pi r to the 4 over 4. I'm just reading it from here. And so if you plug those numbers in, you end up with a magnitude of 10.62 meters. And so this, as you recall, is equal to y sub c plus delta y sub c, as we called it, right? If you look at this figure. Y sub c is the depth of the centroid, the slope depth of the centroid, the slope distance from the surface to the centroid. And this small amount is the offset of it from the point of action. And so those are those two amounts. And so since the slope distance is actually 10 meters, sorry, I wrote that the wrong way around, delta yc plus YR, YC, right, in my terminology. And therefore, this place where it acts is 0.62 of a meter below the centroid. And so we have that. We could do it for the location in R, but let's make our life easier by just noting the fact that it's symmetric as we go across the length in the x direction, and it has to act on the center line that goes through this. So let's not worry about that. But we could do the same calculation. So we have two amounts. So now we have enough to be able to resolve this portion. So if we want to calculate the magnitudes, then we know that this is equal to 0.62 meters. This length here is equal to 5 meters, I think, right? And so if we sum moments about the about the pivot point, then what we end up with is 7,700 times 10 to the 3 newtons times the lever arm, which is 0.62. And that has to be equal to whatever this force, what are we going to call it? The stop force multiplied by 5 meters. And in that, the only thing we don't know is this value here. So that's what this is. Not stop, but S shut. And so we solve for the magnitude of this, and we come out with a value of 954 kilonewtons. And that makes sense, right? This is a pretty big number. This is going to be 1,000 kilonewtons. This is a small lever arm that it's pushing with. This is a small force with a big lever arm. Together they balance. So that's it. So it's a standard result that we can use to get the location of action. So you need to remember, for anything that's under the surface of a compressible fluid that's flat, almost invariably the point of action is going to be either equal to or below the centroid, and more often than not it's going to be below. It would be a rare case where it's equal to. If it was a gas acting on it, it would be equal to. Don't know what this is, don't want to deal with it, same stuff. Everyone get it? So another one. So one more example just to cement the idea. So again, interpreting these questions so you can understand it. Rigid gate OAB is hinged at this point here. It rests against the rigid support at B. What minimum horizontal force do you have to apply here to be able to keep it shut? And so how do we rationalize that? So if we would draw the pressure that's acting on this gate, I'll draw it to a side here. There'll be a pressure here that's acting at this point, which would be equal to this height of water. It would increase with depth along here. And so it would look like this. This would be acting on this side, of course, and it would give you a force here, which we'll call F sub H. They're calling it 1. I'll call it the same as in this. It's drawn below, right? And so what we could do is calculate the magnitude of this force, and we also want to calculate where it acts. And if we look at this point here, I'll draw it off to a side. It's going to be a pressure here. The pressure acting at this point here is the depth of the water multiplied by its unit weight. The pressure acting here is going to be the depth of water by its unit weight. They're the same. And so the pressure distribution is going to look like this, acting downwards, and it's going to be uniform. And of course, the magnitude of this pressure is going to be equal to the same pressure as length of this, right? Geometrically. Bless you. And so this is going to be what we'll call F2. And so what we can do is we can use their expressions that we had before. The horizontal force is going to be the unit weight times the depth of the centroid times the area. So what's the depth of the centroid? This is 3 meters. This is a 4-meter gate. So I guess the centroid is going to be at 2 meters. So this is what we call H sub c. Can you see it? Is it this dark? Yeah, dark enough to see. So this is going to be 3 plus 2 meters, which is this. Unit weight of water. 3 plus 2 meters is H sub c. And this is the area, which is 4 meters down and 3 meters into the page. So this here is the area of the gate. And it gives us a number. It doesn't say where it acts, but it gives us a location. F2 is going to be just the pressure acting at this point multiplied by its area. So the depth of the centroid also is H sub c, which is equal to 3 plus 4, which is 7, plus the area, which is going to be 2 meters times 3 meters into the page. So this is area, unit weight of water. So we have both the magnitudes of the forces. And so now we need to be able to do part 3, and that is look at a failure mode. And the failure mode is that it's going to rotate around this origin. And so we can take the force 1 acting in this direction will give us a moment, which is positive. Force 2 acting by this length will give a second moment, which is positive. And that has to be countered by pressure times P times this length acting against it. And we know exactly the lever arm of this value. And so we can write this equation in terms of the force 1 multiplied by its lever arm, which we don't know yet, which I'll call L1, and force 2 multiplied by L2. So force 1 multiplied by L1, force 2 multiplied by L2, and that has to be equal to P times LP. LP geometrically is 4 meters. So this is LP. And so what we don't know are these two values. And so we have to solve for those. And so these two values will just be our values of y sub r, uppercase R. So we have to go back in and do those calculations. And what will they be? YR for force 1 is going to be the depth of the centroid plus the second moment of area, depth of the centroid, and A. So do we know those things? If I make this smaller. Try to make it a bit smaller. So it all goes on one page. What's what? What's this value? Depth of the centroid is going to be halfway down this. So it's going to be 3 meters plus 2 meters. Ix sub c is a 12th times b cubed times a. A is the depth into the page, which is a. So this is the depth into the page, and this is the height of the gate, 4. So this is what we'd have called b, and this is what we'd have called a on our rectangle in the second moment of area, divided by 12. Y sub c we had before is 3 plus 2. So this is y sub c. And the area of the gate is 4 high and 3 into the page. And so this is this A. And not surprisingly, it gives us the depth of the centroid, which is 5 plus some small amount below it, which is this 0.267. So that's 1. How's it going to work out for F2? So the problem we have with F2 is that the slope length is infinity, right? Because it takes infinity to get to the place on a horizontal thing until you intersect the slope. And so we have to realize that because this is just a flat distribution, the location of action of this is just going to be in the middle. It's the balance point of the beam because it's uniformly distributed pressure. And so Y sub r for this one is going to be a lever arm which is 1 meter inboard from this edge here. It's just going to be half the length. This is be Y sub r 2 if you like. So it's kind of an easy one, but you have to realize that. Do you get it out if you do? I'm not sure. Yeah, let's not worry about it. You have to realize that if it's horizontal, you can make your life easy by realizing that the distribution of pressure has to be uniform across it. And therefore, the location of action has to be just the balance point. And so now we have the length of the lever arm 1. We have the length of the lever arm 2. We know this one is equal to this distance, which is 4 meters. And then the only thing that we need to solve for is the value of the pressure, the force that we apply here, which is 436 kilonewtons. That's it. So it's a bit formulaic. You just need to understand what equations to use. I'm not sure what we do next time. I think we go through some more examples, but you just need to realize how to use it. A few more minutes to everyone get that? Fine. I guess these are looking at simple distributions. If you look at distributions of pressure, there are some very simple results. The most simple result is if your surface is intersected by your wall, the pressure distribution goes to 0 at this point, and it's linearly with depth. The point of action of this is at a depth of 2/3 of h. Standard result. And the reason for it is if you take a triangle and you put that triangle with the point here and the thick end here and balance it over your finger, the balance point of that triangle will be 1/3 of the way up from the thick base. That's where the weights of those. So this distribution of the weight of this triangle, the balance point will be exactly 1/3 up from the base of the triangle, 2/3 up from the apex, 2/3 down from the apex. So that's a useful standard result. You'd also get that result if you used the parallel axis theory as well. You can also get these results by using simple shapes for which you know the distribution and taking moments. And so if you had this inclined plate below the surface, another way to do exactly what we've already just done with the parallel axes theorem, or the second moment of area, is to take this plate and to decompose the pressure that's acting on it into two shapes. One would be a prism, which would be the pressure at the top of the plate distributed across the bottom at the same magnitude to give you this rectangle. And then the triangular distribution, which is the increasing pressure with depth, which relates to the increment that you gain by going down this particular depth to this point here. And what you could do with this is you now know that the point of action for the constant distribution is halfway along its length, which is here, L over 2. The distribution from this triangular distribution is 2/3 down from the top or 1/3 up from the bottom, so L over 1/3. And you could take moments about any point that you want to. It's not any point. You could do it you could extend this up to here, and you could take moments of this force times this lever arm, this force times this lever arm, and you could equate it to the resultant force, which is the sum of these two forces, by some other lever arm. But here I'm doing the opposite. So the other way to do it would be to take moments around this point here. So if you take moments around here, you get the force of the rectangular distribution multiplied by this lever arm L over 2. You have the force for the triangular distribution, which is 2/3 L, which is F triangle multiplied by 2/3 L. And that has to be equal to the resultant force multiplied by some unknown lever arm. So this is what you'd like to get. And you know that this resultant force is just the sum of F prism and F triangle. So you have those amounts. And so if you have all of these amounts, the only unknown in this is the lever arm. And I guess you'd find that the actual point of action is somewhere in between these 2 points. It's not going to be outside, can't be outside. So that's that. And then I guess the final coup de grace is that we've talked about absolute pressures and gauge pressures. It's probably easiest for us to work in gauge pressures and take the pressure at the top of a lake as being equal to 0. That's what we feel 101 kilonewtons per meter squared in our ears, but we assume that's 0 just because it's our reference. So if you're looking at the pressure that's acting against a gate, if we do it in gauge pressure, it's 0 here and it increases linearly with the unit weight of water. If we do the calculation in terms of absolute pressures, then this pressure here would be 101 kilonewtons per meter squared plus the change in the unit weight of water. But acting on the other side of this gate is 101 kilonewtons per meter squared. And so this, if I use my handy dandy color, this area here exactly cancels with this area here. And so we're left with this, we only worry about this triangular distribution. And so if we're calculating the net force that acts on this gate, because atmospheric pressure acts against this, and we're assuming that atmospheric pressure is 0 as gauge pressure, then we're just worrying about this triangular distribution of the liquid pressure that acts on the gate. Okay? That's it.